Okay, off we go. So last time, we just barely got started in section 3.4. Let me remind you roughly what the point of that was. We had this thing called the gradient, right? And the gradient is a vector whose components are partial derivatives, but the very first thing we did is reinterpret that as the result of applying this sort of vector operator, if you will, to some function, right? So we're going to reinterpret that symbol as being this thing we call the del operator, and when applied like so to a function, it gives us something called the gradient. So now do be careful to point out that this symbol right here does not mean gradient, right? There are many things that we're going to do with this thing, not just compute the gradient. So it's only a gradient when you talk about the result of applying it in this way. We're about to do some other things with it. So this is the del operator. Okay, so the very first thing we're going to do, now again, I'm going to start with the same apology I gave you last time. I think this material is kind of premature. I can't give you much of a context or motivation for what I'm about to claim. And that's not really not how math should go, right? I mean, I think math should be a kind of follow your nose. Seems like reasonable decisions to make at the time. Everything follows from what we had just done previously. That's the ideal. The reason that we're going to do this, the reason that the book did this, and therefore the reason we're going to do it, is because it plants a thought and allows you to have some time to kind of chew on it and digest it and kind of get accustomed to it. So here we go with that apology. So the big idea is we're going to take this del operator that we had just talked about, that consists of various partials. Correction, various partial differential operators. We're going to do a dot product with now a function. Correction, not a scalar valued function, a vector field function. And now interpreting a dot product as we do, right, we're going to apply the first coordinate to the first coordinate, second to the second, third to the third, and add them up as one does with dot products. And so this dot product, I mean, if you just kind of write it down as it seems it ought to be written down, this is what we end up writing down. So it turns out that this expression that results from doing a dot of a del operator with a vector field, it turns out this is actually something that's really interesting, really important, not just mathematically, but also in physics and engineering. And this is really one of the big ideas. In fact, I asked one of the engineering professors one time, okay, let us know what's most important to y'all for students to know about multivariable calculus. What should we focus on? And she enumerated with great emphasis a short list of things, and one of them was this, right? So this is going to be a big deal for a lot of y'all, and independent of that, even if you're not engineers, it's going to be a big deal in this course. All right, now, most of what we're going to say about this thing, which, by the way, this expression with this notation is called divergence, right? Most of what we're going to do about this will come up in chapters 6 and 7, mostly 7. But there's a lot going on in those chapters, and so again with the preview, again with the planting of thought, letting it stew, letting it soak in your head. So what I'm going to do for now is, against my sense of right, I'm going to just make a completely bald assertion with no justification, and I apologize for that. There's no way around it. This is the idea. Divergence, what it's going to represent physically, geometrically, is when you interpret the vector field as representing the flow of a fluid, it's going to represent the extent to which the fluid is flowing away from where you are, loosely speaking. Now, let me try to communicate that more effectively with a specific example. So here's a vector field. The vector field, let's see, color choices. The vector field is that right there. We've discussed that vector field before. It looks about like this. Right? And to that vector field, I'm going to take the divergence right? And keep in mind, divergence means dot with the del, or use the formula there above, which of course turns out to be this expression right here. And if you just compute those partials, they're really easy partials, and just kind of punch it up, what you get is 3. Okay, now what does that mean? And does that track with the claim that we made, right? The claim was that divergence should represent the extent to which the fluid is flowing away from where you've computed it. Well, we just got through computing divergence at the origin. Now, as it happens, it doesn't. The fact that we were computing it as the origin didn't really come up in the arithmetic because, well, it's a constant. So what we're about to say applies everywhere, but it's harder to see everywhere. But let's just focus on the origin. At the origin, indeed, the fluid is flowing away from the general vicinity of that point. So that's kind of the idea. Everybody on board, sort of? I mean, again, there's a tremendous amount of sloppiness in how I'm describing that. That's again, not happy about this, right? But that's where we are. That's what we have to work with, and this is the big idea. Okay, all right. Now, this doesn't prove anything, of course, and I will give you much more persuasive arguments that this is how you should think about divergence later in the course. Okay, so now let's real quick aside, what does this mean physically and how should I visualize this sort of physically? I'm going to suggest that there's a couple of different interpretations of what this might mean physically. So one possibility is that there's a certain amount of fluid in space, and that fluid is all just kind of flowing outward away from the origin. And now let's just think about that practically speaking, right? What if this was a fluid of fish in the ocean, right? If this is how fish are swimming in the ocean, I think there's going to be less fish at the origin after a certain amount of time passes, because the fish are all flowing away from there, right? So there might have been a certain density of fish, but then as time passes, there's less fish because, check it out, they're all leaving. So one possible interpretation of this is that this is pointing to how the density of the fluid, whatever that fluid is, how that density of fluid is decreasing. Could be. That's one interpretation. Now, it's not the only interpretation. Here is an entirely different interpretation. Maybe there is fluid being spontaneously generated right there. Right? So a couple different possible ways that could happen. So forget about the ocean. Let's talk about in the atmosphere, and somebody's set up a little chemical reaction that happens right there at the origin, and this chemical reaction generates a gas, and it's literally generating this gas. Well, that gas has got to go somewhere. It's going to go outward from where it's being generated. So it could be that there is a rate of change of density, and the density is decreasing, or it could be that the density is not decreasing at all. It could be that this is what results when you generate fluid. It's a different kind of fluid, different scenario, right? So one thing to keep in mind is when you're thinking about divergence and what does it mean physically, you have to understand what kind of a fluid are you talking about. What are the physical properties of that? How does that fluid behave? And you have to make sense out of divergence in context to decide which one of these are you actually looking at. And just a preview, if you all take a fluid mechanics course or something like that, what you're going to also find, and I'll hit this again a little bit later when we have more context, it could be a combination of these, just a heads up. So there's that too. Okay, yeah.
If it was negative, then would that mean that they were going towards?
Yeah, absolutely. In the this sense, yeah, absolutely. Yep, right. Yes, and all the arrows would be, let me not overstate it. It's not that all the arrows would be pointing inward, but it would be that some combination of these would be, some combination of the exact opposite of these would be true. Yeah. Okay. So here's another example just to show that this kind of tracks with our intuition. Vector field, here's the picture, good example to think through. Make sure you can persuade yourself that this is the right picture. Perhaps even make sure that you can persuade yourself that you could generate this picture as needed, right, from that formula. There's some thinking to do there, and it's a good thing to kind of chew on. So again, with that in mind, this vector field, if you take the divergence, compute that divergence. Again, it's easy partials, and it turns out that divergence is 0. And I claim this kind of tracks with our intuition as well, because, when I look at some little region, and again, let's just focus on the origin, even though the divergence is constant. Doesn't matter. That little vicinity of the origin, sure, there's fluid going into it. Sorry, I wanted to get into pencil mode here. There is fluid going into it, but there's just as much fluid going out of it. Right? You look at these flow lines, and that which goes in also goes out. Or on the other side, down below the x-axis, that which goes in also goes out. So in the net, the fluid isn't really flowing inward or outward. It's doing both, and therefore neither, right? It cancels. Altogether, you're not expecting the density of fluid to be changing here. This doesn't suggest that fluid is being generated, right? No chemical reaction has been set off here to generate fluid that flows like this. So again, this kind of tracks with what you would sort of expect from looking at the picture. Okay. All right. Next example. Another weird expression that I'm going to write down that we have no context for, but that we eventually will. And I'm doing this unpleasant task of planting the thought without any context, just so that it can have a time to bubble, right, in your heads. This one, again, is something you do to a vector field. Here, again, what we're going to do involves the del operator. There it is. And what we're doing in this case is we are crossing. We're not dotting them. We are crossing them. And remember, a cross product... Right? A cross product says you're going to take the determinant of the symbolic matrix that you get when you put the standard basis vectors there, and then the one on the left goes in the next row, and the one on the right goes in the last row. So just kind of following our symbolic rules for how a cross product works, you get this expression. And now... that's not a matrix, right? This is something passing itself off as a matrix, but it's kind of nonsense because the elements of a matrix are supposed to be numbers. That's a vector, that's not a number. That's a differential operator, not a number, right? So this is sketchy, right? But we've seen sketchy before. We've talked about the idea of a symbolic expression, and so, roughly speaking, the big idea here is pay no mind to the fact that this is a bunch of nonsense, as written. Just write down what you think this should mean based on how these computations go, and you will get what turns out to be exactly the intended expression here. And it's a big formula that I don't want to write down. There's no particular point in writing it down. Okay, so all of that said, if you compute this out, you get some... you get a vector, and completely unjustified, completely without context, all apologies. Here's my assertion as to what this means. What does this look like? This thing called curl. I mean, in some loose sense, it tells you how much and around what axis there is what we call a circulation of fluid. So it's not about the extent to which fluid is flowing outward, it's the extent to which fluid is kind of rotating or turning, you might say, something like that. Right? So we call this circulation. And now, by the way, again, this term circulation will come later. I can't define it now other than it's roughly kind of the extent to which there's a twisting or a rotation hidden inside the fluid. So that's my claim, completely without justification. Again, let me try to persuade you as poorly as possible with just a couple of examples that at least track with this claim. And here we go, vector field right here. We've done something like this vector field previously. This is the stirred pot. This is a three-dimensional version of the stirred pot. I'm recognizing that pots really are, they have height, right? So the rotation is just not, it's not just at the top of the pot of water. For all different values of z, there's this kind of horizontal rotation, if you will. Okay. All right. So that said, let's compute the curl. Here's the notation, here's the expression, and if you punch this up, now again, there's a determinant, so you're going to look at three, you go across the top, E1, E2, E3. For each one, you look at the corresponding submatrix, and you take the appropriate little determinant, the appropriate little partials of, you just crank it out. And what you will get is this expression right here, which is, of course, a vector pointing vertically. And I'm going to claim that that actually tracks with the assertion that I've made here. So the assertion was that the curl is going to tell us how much and around what axis. Well, this curl vector is pointing vertically, thus suggesting a vertical axis. And sure enough, the circulation of the fluid, as you would imagine it would be based on, of course I still haven't defined circulation, but if you know what I'm talking about, the fluid is kind of going around like this, and sure enough, it is going around the axis that the curl claims that it is. That kind of tracks. Is that cool? No justification, no context. I'm sorry. That's what we've got here. That's what the book has done, and pros and cons pedagogically. Yeah.
If it was negative 2, would we go in clockwise?
Yeah, that's okay. Exactly. So the which direction it's going is, and we're gonna see this later on, right? But right hand. So thumb in the direction of the curl vector. The direction that your fingers kind of want to curl around your thumb suggests the order, the direction that it's going. Yeah, totally. Yes.
Just to confirm, it doesn't have to be like the axis doesn't have to be X, Y, and Z.
Correct. Oh, yeah. There are sometimes the curl is pointing that way. Yeah, absolutely. And that suggests that the fluid is kind of rotating around that axis. Yeah, we'll see more examples of weirder. Again, my purpose here is to not to tell you everything about curl because there's too much and there's a better time for it. But I just kind of wanted easy, convenient, relatable examples. Yeah. Okay. All right. Now, how much is this fluid rotating? How powerful is this tornado? Right? We've got this vector field here, and you can see that there's a rotational aspect to it, and this is a whirlpool or a tornado or, dust devil, whatever you want to call it. How do we quantify how strong those are? I'm going to say that's somebody else's problem, right? So being precise and picking units and that sort of thing. But what we're going to find, and I'm just going to claim this, is that the longer these vectors are, thus suggesting the faster the fluid is rotating, the longer the curl vector will be. And so, let's not worry about units. There's a sort of a constant factor or units or however you want to think about it involved. And that's a detail that we don't need to worry about. But the longer the curl vector is, the faster the rotation is. That's all we need. Okay. All right. Here's another example. Oh yeah, sorry.
I have a question about the 2. So what is the 2 then? You saying?
Well, yeah. So the two is
right?
the 2 is telling us the magnitude. The magnitude tells us how fast the tornado is going.
How long the thing is, kind of.
I mean, keeping in mind that each one of these vectors represents a velocity. It's vaguely related to how fast is the fluid. I don't want to get into the weeds.
Okay.
That's weeds, right? But the longer this vector is, the stronger the tornado is. So this is a Category 2 tornado, if you will. I mean, again, super sloppy. If the curl had been 0, 3, 4, that would be a Category 5 tornado because the magnitude's 5, if you will. Is that satisfying? Yeah. Again, this is the kind of price that we have to pay when we do material out of order. So I'm sorry that it's there's a bunch of hand waving going on here. Okay, now let's look at this picture right here, and I think I could probably persuade you that as the fluid does what this says, as per this picture, and thus moves in these lines like this, there's really no circulation happening here. The fluid isn't going around. There is no rotation. All right? Where's the rotation? So this vector field here, if we compute the curl, we should expect to get 0. And we do. So again, it tracks. This doesn't prove anything. This is somewhat satisfying. Okay, now here's the next example is to dispel a misunderstanding that happens a lot. A lot of people look at the circulation, the obvious rotation that we see here, and think that what we're talking about is the fact that the flow line is a circle. That's actually not what we're talking about. Seems like that's what we're talking about, but it's not what we're talking about. So this circular flow line does, as it in this case does, turn into an actual circulation of fluid. There is a rotation. You can see the rotation, but it's technically not, the point here is not that there is a circular flow line. So what I want to clarify this by this next example. Let's look at this vector field here. And again, make sure you can produce these pictures. We get a flow line that looks like that, and another one like that, another one like that. Again, we're seeing all straight lines with the flow lines. And yet, if you compute the curl, per the usual formula, you don't get 0. So this is kind of a what gives, unsatisfying, I'm not happy, this is not consistent with what it was supposed to be, so we feel. Okay, so the point here is that we are misinterpreting what I mean by a rotation. I'm not saying that the individual particles of fluid are themselves going around in a circle. What I'm saying is that there is a rotation in some sense, and here's the rotation that I want to claim. If you were to encounter a body of water of some sort that this is the surface of, and if these arrows were to represent how the water is flowing at that surface, it's flowing one way on one side and it's flowing the other way on the other side. And if you were to drop a leaf into the water right there, well, that leaf is being pushed that way on that side, but it's being pushed this way on that side, and what do you think is going to happen to that leaf? And my intuition is that that leaf is going to be rotating. In fact, I think it's going to be rotating what you might call clockwise, as we see from above. And if it's rotating clockwise and following my asserted right-hand rule, clockwise would suggest a curl vector that should be downward. And sure enough, the curl is downward, non-zero and downward, because there is a rotation. It just doesn't manifest in the behavior of individual particles of fluid. It manifests in how those interact with some object floating in it. Yeah.
Yes, if we're asked to draw the vector field, how would we determine if the vectors are anti-parallel or like if they're moving on circular planes?
If the what now?
Like if the vectors, how would we determine if they're like anti-parallel? As in like if they're moving opposite directions or whether they're forming like a circular.
So you're wondering how would you use the curl to distinguish this example from this example? You wouldn't. Yeah, the curl alone doesn't distinguish between these. So in both cases, the leaf that you drop into the water rotates, and that's all curl tells us. Yeah, so if you wanted to distinguish this from this, you would need other tools, such as you could actually write down the flow lines, right? You could write down the differential equation, system of differential equations, solve, find the flow lines. Here you'd get straight flow lines. Here you would get circular flow lines. Yeah. So curl is not the be-all, tell-all of everything. It just tells us this one thing. Yeah. All right. Okay, so heads up about this point in particular. There is a homework exercise. I've got to confess, I don't remember where I put it. I think I may have put the relevant homework exercise in the Chapter 7. It's one of the AHPs, so it's one of the exercises I wrote myself. And that exercise turns on this example. So this is something to make sure to digest. Okay, so we've talked about divergence, we've talked about curl, we have previously talked about gradients, and it turns out, and this is, by the way, we're about to dip our toe into some really deep waters. This is extremely sophisticated mathematics. This is stuff that Gauss himself never knew, right? So this is modern, recent, like less than 100 years old math, which obviously I can't tell you the whole story, but cutting out all the formality and the rigor and the abstraction and just cutting it down to the bare bones, how do these things kind of in some sense relate to each other? It turns out that it's very natural to compose those operators in this order. And what I mean by natural is that when you compose these operators in this order, shockingly interesting things happen. Now keep in mind, when you take a gradient, that turns a function into a vector field. When you take a vector field and look at its curl, that produces another vector field. Right? You look back at the formula. And when you take a vector field and compute its divergence, that gives you a scalar valued function. Oh, my apologies. So you can compose them in this order, and it turns out that what happens is you get something called an exact sequence. That's terminology you don't really need to know. The punchline is everything has a lifetime of 2. There is an exception, a couple of exceptions, and I'll quickly wave my hands at those. And I don't want to get lost in the weeds on this either, right? But broad strokes, silly counterexamples acknowledged. Everything has a lifetime of 2. And so, for example, what do I mean by that? If you take a gradient of something, a function, of course, so starting on the far left, if you take that gradient, and then if you compute the curl of that, you will get 0. And this is what I like to call a lifetime of 2. I think of this as born here, died here, lifetime of 2. Don't overthink it. Right? Is everybody okay with that? It's kind of satisfying in some sense. Just a metaphor. Doesn't mean anything. Okay, here's another version of the lifetime of 2. If you have a vector field whose divergence is 0, so you take the divergence of that vector field, and if you get 0, then it follows from that vector field is the curl of something else. And so, again, some people like to throw out this possibility as a counterexample to the lifetime of 2. Hey, look, I got a vector field. The divergence is 0. It died after one step. No, it didn't. It wasn't born here. It was born back here. and it died after 2 steps. Lifetimes are always 2. Now, that's a heck of a pattern, right? That's what we call an eyebrow raiser, right? How about that? That's weird. Why is this the case? What's going on underneath, behind the scenes that makes this seeming shocking coincidence happen? Deep water. There's really heavy stuff going on down there. And that's stuff that we won't really be able to see in this class. But even though we won't understand why this pattern holds, it is very valuable for y'all as students in this course to know that this pattern holds. And we're going to make tremendous use out of this pattern, even not knowing where it comes from, but we're going to make tremendous use out of this pattern when we get into chapter 7. 6 and 7. Anyway. Okay. All right. Okay, so, So chapter 6 and 7, more to say about this. Okay, so that's it for chapter 3. We move on now to, you'd think chapter 4, but no, we're skipping 4 and doing 5. I want to say a quick word as to why we're doing that. You'll have heard me say a million times that this course is packed. We have a tremendous amount of material to cover. Here's another thing that you may have heard through the grapevine, right? The buzz on campus. The last part of this course is where it gets really challenging. It's the most interesting. It's where there's the most various connections between different things. There's a lot going on in chapters 6 and 7. So I think that one of the really important things in teaching this course and students learning this course is that they have as much time as possible to be able to digest that material in chapters. That material in chapters 6 and 7, right? So how am I going to give y'all more time to digest chapters 6 and 7? Well, I'm going to do that by shifting it as early as I can in the course. Now, here's the problem. Chapter 6 and 7 relies pretty heavily on chapter 5. Chapter 6 and 7 relies pretty heavily on chapter 3 and on chapter 2 and on chapter 1. It has to come after pretty much everything. I can't move it earlier, except for one thing, and that's chapter 4. Chapter 4 is the one part of the course that isn't at all necessary to make sense out of chapter 6 and 7. So I pushed chapter 4 to the very end to help us push chapters 6 and 7 back, or I guess I should say, up, to push it earlier into the course so that you can have as much time as possible to digest chapters 6 and 7. So, anyway, there's that. Okay, so chapter 5, integrals. Y'all will recall when we started chapter 2. We started with partial derivatives, and I complained about it. Because partial derivatives, they're easy. They're relatable. But, looking back as we now have the benefit of seeing all the rest of the stuff in Chapter 2, ultimately, that's not how you should think about derivatives, right? We have this much more general, ultimately natural idea of a multivariable derivative that, the input changes are velocities, the output changes are velocities, and the thing that relates them is the derivative matrix. The derivative matrix is ultimately how you should think about multivariable differentiation. And partial derivatives were a convenient computational tool, but they're not the point. They're not the protagonist of that story, right? They're incidental. So I pointed this out in advance. I didn't want anybody, getting too comfortable with the idea that partial derivatives are where they should hang their hat in differentiation. So I'm going to give you the same story here. We're going to start with, when it comes to integrals, we're going to start with something that's eventually going to be useful, but very importantly, not the way that you should, when you're thinking about integrals as you leave this course, or when you are thinking back to this course in the future, you should not be thinking about what I'm about to show you. This is a foot in the door. And then a minor tool that we'll use as well. Okay, so disclaimer done. here's the big idea. I'm going to go back to single variable calculus again. Again, kind of flashbacks to chapter 2. Y'all will remember this idea of computing the volume of a rotated surface. One of the standard examples in a single variable calculus course on integrals. And you can compute that volume by breaking the volume up into little pieces of volume dV, and then you add that up over all the slices. And then, hey, good news, I can tell you what the volume is of that individual piece there, because it's an area times a thickness, and the thickness is easy. Oh, let's see here. I'm making bad color choices. The thickness is just dx, and then the area, nothing to it. That cross-sectional area, it's the area of a disk, garden variety, shape of geometry, right? High school geometry, pi r squared, the r is the value of the function because it's the height on the graph, and, you know, all that. Cool? Everybody remember that from way back when? All right. Okay. So I'm going to say, roughly speaking, the lucky break in all of this is that we happen to know the cross-sectional area. It happened to be, like I say, garden variety, you know, geometric shape that middle school students know how to compute the area of. Okay. All right, so now we're going to consider a different scenario. Now we're going to look at a graph, and as y'all know, I think it's important to make a big deal that we're looking at a graph specifically, right? So this is going to be part of our calculus of graphs. You're looking at a graph of a function of two variables, and suppose you're given a rectangle down in the domain, if you will. So given the graph surface and given the rectangle in the domain, we can ask the reasonable question of how would I compute the volume under the graph? How would I compute this amount of volume right there? Yeah? Reasonable question. You might say this is kind of a one dimension higher version of the first question that everybody deals with when doing single variable integrals, right? Area under the graph. It's the very first example everybody does. So this is just one dimension up, volume under a graph when there's two instead of one input variables. Okay. All right, well, so I'm going to rip off the idea that we just did above. I'm going to say that the whole is the sum of the parts, and I can look at, for example, this little slice of volume right there. I like metaphors. I like to think of this as a loaf of bread, and that's a slice of bread, right? So the total volume of the loaf is the sum of the volumes of the slices. Believable? We're going to add up over all values of, well, it looks like y is going to be going from c to d, so that's how I'll be adding up all those for all values of y between c and d. And then the question just comes up, how do I compute this volume? Right? What's that equal to? And here's where we hit a kind of a roadblock. In the analogous calculation over here, how did we compute this volume? Oh, well, that was area times thickness, and area was easy. Area was a disk. It's, again, a formula we've all known for years. Here, the cross-sectional area is not a disk. It's not a rectangle. It's not a triangle. It's not a parallelogram. It's not a rhombus. Think of all the formulas that you know for how to compute areas of from high school geometry. This isn't any of them. So, a lot of people would throw up their hands and say, well, game over. I guess this didn't work. Let's just bail. Right? Very tempting. Okay, so here's the big idea, the very clever idea. Very clever idea is to press on anyway, realizing that, in fact, this curve here, we are simply looking to find the area under that curve. And, of course, that expression. Area under a curve rings a massive bell for everybody, right? Area under a curve. Now, wait a minute. We need for that curve to be a graph. Okay, so is this curve a graph? Well, in fact, yes, it is. This curve is a graph with the understanding that we are fixing a value of y that is not allowed to change and therefore is a constant, and therefore, as far as this area is concerned, not a variable, right? What we've got here is a curve where height, z, is a function of one variable, x. And this is literally, no asterisk. That curve is the graph of this single variable function that you get when you, as we've clearly indicated here in the diagram, chosen to view a single constant fixed value of y. Let me pause on this before we reap the benefits of this observation. Is everybody comfortable with what I'm doing here? Yep.
There would be an example where the cross-section is not a function?
Oh, there's always counterexample. If I have a sufficiently contorted function f, then So yeah, we're going to assume here that f is continuous, and if f is continuous, then this will. It might be a weird graph. The graph might be a weird curve, but it'll be a curve, and what I need is the area under it. And if it's continuous, then that's perfectly fine. Yeah. Right. Okay. All right. So here we go. We have a graph. How do we find the area under a graph? We do an integral. And so let's see here. Let me go back to my colors. So here's the area I want to find. The area is an integral. Now let's be careful to notice that in this integral, we're viewing height, z, as a function of how far we move along kind of, if you will, the base of that area we're interested in. Namely, we're going to view height as a function of x, and so our little widths are dx as I'm computing that area. Yeah? There's a momentary little sort of confusion. Wait a minute, I thought it was dy. Well, yeah, no. What we're doing as we slice up the loaf of bread, the area that we're currently computing is going to eventually get multiplied by dy to give us the volume. Yeah, sure. But that's not what we're doing right now. Right now, we're interested in finding what the area is that I will eventually multiply by dy, and in the computation of that area, these little thicknesses are dx. And so now you put the pieces together. This is just Legos at this point. We have the area of the cross section. Let's see, I already had that as blue. This area is an integral. That's the area of the cross section. Area times thickness. Oh, let's see, let me do this with a pencil. Area times thickness. Right, thickness in the y direction is what gives us volumes, right? And I'm adding that up. Let's see here, color choices. We're adding that up over all values of y from C to D. And that gives us the volume. So it is a little creepy. It's a little confusing. We are using an integral to compute the volume in question, but we're computing an integral of a formula that didn't come to us by way of high school geometry. We're computing an integral of a formula, an area formula that came to us by way of, well, another integral. So it's an integral of an integral. Yeah? All right? All right. Okay. So a little bit of terminology. So this being, you take an integral and then you take another integral. They call this an iterated integral. I've always kind of bristled slightly at this terminology. To me, iterated means you're repeating the same process multiple times. I believe that this is not what we're doing. It is an integral of an integral, but it's a very different integral of a very different integral. So I prefer the term nested integral It's another one of these terms that I'm kind of trying to popularize. We'll see if it takes off. I'm going to take credit if it does, but it hasn't. So anyway, iterated integral is the term, and imperfect though it is. And then there's other little bit of terminology we need to worry about. If there's two integrals, there's a temptation to call one of them first and one of them second. And that's a problem. Because as you're writing down the integrals, right, we wrote down the dy integral first. The big picture was that the volume is the sum of the slices of bread, and so dy integral. But when you come to computing this expression, when you're going to compute, I can't start by computing the dy integral because I don't even know its integrand yet. The integrand is the dx integral, so you have to evaluate the dx integral first. So which integral is first really depends on your kind of point of view, and that's really bad terminology, right? Extremely confusing. So please don't talk about which integral's first, which integral's second. That's ambiguous. What very conveniently is not ambiguous is to point out that one of the integrals is on the inside, right? And one of the other integrals, one of the other integrals, the other integral is on the outside. So please do be careful with that. First, second does not make sense. It doesn't mean anything, and if you write it on an exam, I don't know what you meant. Right? Okay, yes?
If you have 4 variables, you have to do
Oh, God.
3 separate integrals.
Oh my God, we're doing double integral, just two variables only right now, and we will eventually work our way up to 3 variables, and then I might wave my hands at an integral with more than 3 variables, but it's very difficult to visualize what that would even mean.
So is
Yeah.
it 3? Is it going to be 3 integrals?
Yes, but that's way premature. So for the moment, yeah, no, you're great. I'm glad you're curious, but that's better left for another day. Yeah. So for right now, we're considering only volume under a graph of a function of 2 variables. That's it. Yeah. Okay. Okay. So I just want to get an example under our belts before we call it a day. Here we go. We want to compute the volume under a graph. Here's the function whose graph we want to find the volume under. Here is the rectangle over which we want to compute that volume. Let me talk about this notation a little bit. This is notation representing, let me zoom. Oh, come on. You can zoom. There we go. This represents this rectangle right here. And the notation comes from the idea that the first interval there is telling you what the range of values of the first variable x is, and the second interval listed is telling you the range of values of the second variable y. So I think you'll agree that's a very compact and handy notation to represent a rectangle in the xy plane. We're going to be using that notation a lot, so make sure you're comfortable with that meaning this. Okay. All right. And with that noted, a lot of this we've already got done. We already argued that the volume under a graph is the iterated integral. Yeah.
Can you do y first and then x? Because
We are here doing x first and then y. Oh, you mean in this notation? Or do you mean with the integral?
with the
Yeah, I'm going to address that question later.
Okay.
So for the moment, I just want to keep us focused on this exact example here. Yeah, the short answer, yes. But let's keep our focus. Okay, so we know volume is this iterated integral. We know that the range of values of x is 0 to 1. So x goes from 0 to 1. So our x bounds are 0 to 1. We know that y goes from 1 to 2. So our y bounds are 1 to 2. The function is x squared plus y squared. So that goes there, right? And now plug and chug. The one little tricky bit, well, there's 2 little tricky bits. Okay, 2 little tricky bits. The first one is when you're thinking about the inside integral. You're looking at this integral right here. don't forget where that came from. That came from this picture here. And as I was computing this inside integral, I was computing this area for which y is constant. Right? So when you're computing the inside integral, the outside variable is constant, and therefore you should treat it as a constant. Right? Now it's easy to lose track of this point, but let's come down to here, and you can see this happening. As I do this inside integral, notice that y will be treated as a constant. In particular, what is the antiderivative of y squared? Don't fall for the temptation to think, oh yeah, I remember that formula. It's the power rule. It's like 1/3 y cubed or something. No, it's not. Y is a constant. You have to treat the y as a constant. This is just a weirdly written constant. And we're taking an integral with respect to x. And when you're taking the antiderivative of a constant with respect to x, you just get that constant times x. Everybody good? So this is the first landmine that students will step on. So you always have to make sure to be very, very careful to think about which variables are playing what roles. Now, of course, while we're here, I'll just point out that the x squared anti-differentiates exactly like you think it is, because the antiderivative is with respect to x. Real quick last thought so we can wrap this up. These bounds go here. That's what you plug in. Just make sure to be careful. This is what you plug in for x specifically, not y. It's really easy to accidentally plug in these values for what you see as being the variables. These are specifically for x. You plug them in only for x, not for y. And I like this little notational hack to help me remember that. See y'all later. Have a good one. Okay. Let's see.
Whoops.